Alright everybody, welcome back. In this video we are going to work through Technique 3. So we're into the Using Integration by Parts Part 2 lesson related to Section 6.11 of AP Calculus BC. In this we're going to continue with a third integration by parts technique, something known as solving for the unknown integral. This isn't something that comes up a whole awful lot, but it's nice to know how to handle it. And this is a technique that we use when we have an exponential function paired with a trigonometric function. Because with integration by parts, what happens is we always set it up so that that du is something that eventually disappears. But no matter how many times we take the derivative of either an exponential or a trig function, they never really disappear. So here's how it works. We want to keep the original integral on the left-hand side of the equation. This is different. We never actually wrote these as equations before. We just kind of simplified. So we want to keep the original integral as the left-hand side of the equation. And then the right-hand side is going to be our uv minus integral of v du. What will happen is the right-hand side will contain something that requires a second application of integration by parts. After we apply parts a second time, the integral v du on the right-hand side of the equation is going to be the same as this original integral, or some multiple of the original integral. Okay? Then we're going to add and divide, and that'll get us to our answer. So let's take a look at what this looks like. So here we've got, we'll use u equals e to the x, and dv equals sine of x dx. And so du is e to the x dx, and v is the opposite of the cosine of x. Alright, so on my right-hand side, now I have u times v, so that's minus e to the x cosine of x, minus the integral of v du, and since I've got a negative sign in here, I'm going to change that to a plus. And there is our first step. Now, we still have an integral here that requires integration by parts. So we're going to apply integration by parts again to that integral. We've got u equals e to the x, dv equals cosine of x dx. So du is equal to e to the x dx, and v is equal to the sine of x. And so this turns into, still keeping my left-hand side of my equation, negative e to the x cosine of x plus u times v. Actually, since I have a plus sign there, I don't really need these parentheses. It's just going to be uv minus v du. So I've got u times v, that's e to the x sine of x, minus the integral of v du, which is e to the x sine of x dx. And now hopefully you notice that the left-hand side of this equation matches this integral right here. That's the official sign that we are done with calculus, well, almost, in this problem. So I need to add e to the x sine of x to both sides, which then makes this 2 times the integral of e to the x sine of x dx. When I move that integral over to the left-hand side, I need to introduce my constant of integration here, since my constant of integration happens whenever I'm done taking all the integrals in a problem. By moving that over, I'm done taking integrals on my right-hand side, so I introduce the constant of integration. And then there's one last thing for me to do, and that's some basic algebra. Since 2 times this integral is equal to this, that means I can get the value of this integral, which is what we were trying to find to begin with, by dividing both sides by 2, or multiplying by 1/2. And so this whole thing divided by 2. And there's the value of the integral that we were trying to find. All right? Example 2. Find the integral of e to the 3x cosine of x dx. Again, we've got an exponential and a trig function. So we'll go ahead and we'll set up the left-hand side. And we'll find our u and our dv. And we'll get to work here. du is equal to 3e to the 3x dx. v is equal to sine of x. And so this is equal to e to the 3x sine of x minus the integral of v du. I'm going to bring the 3 out in front. And that gets me to there. All right, and now I have another integral that I need to use parts to integrate. So u equals e to the 3x, dv equals sine of x dx, and so du is 3e to the 3x dx, and v is equal to the opposite of the cosine of x. All right, so integral of e to the 3x cosine of x dx is equal to e to the 3x sine of x minus 3 times this quantity, uv, which is negative e to the 3x cosine of x, minus the integral of v du. So let's see, I've got minus a minus, that becomes a plus. I'm going to bring the constant out in front as well, and I'm left with e to the 3x cosine of x dx. All right, now I'm going to go ahead and distribute the negative 3 through the parentheses before I do anything else. So that gives me e to the 3x sine of x plus 3e to the 3x cosine of x minus 9 integral of e to the 3x cosine of x dx. Notice my integral here match. So I can add these 9 integrals of e to the 3x cosine of x dx to both sides, which makes this 10 integral of e to the 3x cosine of x dx is equal to e to the 3x sine of x plus 3e to the 3x cosine of x plus my constant of integration. And then lastly, I'm going to divide both sides by 10. And I'm going to write it differently this time than I did last time, just to kind of illustrate there are multiple ways that we can appropriately write these concepts. And boom, there's my integral. So that's the integration by parts technique known as solving for the unknown integral. Let's introduce you to your fourth technique, which for those of you who did not like the last example from video 2 because it got a little monotonous, this will make you very happy. Technique number 4, what is known as tabular integration. We usually use this with any higher degree polynomial. Usually I start using it with the third order or higher when it's paired with an exponential or a trigonometric function. And I set up my table for tabular integration a little bit differently from where you might see it in other places. I organize my information into 3 columns. The leftmost column contains u, whatever our u is to start, and then we're going to take all the derivatives and put them of u and put them in that column. And we do that until we reach 0 at the bottom of that column. The center column contains alternating plus or minus signs, starting with the plus sign. The rightmost column contains dv and all of its integrals. We'll make this list long enough so that the number of terms in the dv column is the same as the number of terms in the u column. So it's important that we do this until we reach 0 in our u column. That way we get all the terms we need from the dv column. After we've completed this, we're just going to multiply down the diagonals to get the terms of your final answer. This is a very cool method if you've never, seen or heard of this before. So we set up our table. I set up 3 columns here: u and its derivatives, dv and its integrals. I put my u and my dv in the same line, and then I skip a line and then do my middle column with my plus sign, my minus sign, my plus sign, my minus sign, my plus sign. So looking at my original problem, my u was x to the 4th, my dv was e to the x, so I put those at the top of each column. And then I go to the next line, and I start with my plus sign. And then in my next row, I've got the derivative of u. The derivative of x to the 4th is 4x cubed. I've got my integral of dv. My integral of e to the x is e to the x. And I continue down in that fashion, and usually what I do is I just fill in my u column right away with the spaces for my signs and go through and find all those derivatives. Derivative of 4x cubed is 12x squared, derivative of 12x squared is 24x, derivative of 24x is 24, derivative of 24 is 0. That tells me where my table should stop. And then I take all the integrals along this side. And now I have all of this information. And for those of you who remember, we watched the movie Stand and Deliver last year in AP Calculus. This is where the tic-tac-toe comes in. We're basically taking this and we are multiplying down these diagonals. So I'm taking x to the 4th times a plus sign times e to the x. And that gives me my first term, x to the 4th e to the x. Then I multiply down the next diagonal. 4x to the 3rd times a minus sign times e to the x gives me negative 4x to the 3rd e to the x. That's my next term. Then I multiply down the next diagonal. 12x squared times a plus sign times e to the x gives me plus 12x squared e to the x. You see that there? I'm not even going to bother to highlight it. Then my next term comes from going down this diagonal. 24x times a minus sign times e to the x gives me negative 24x e to the x. Gives me that term. Multiplying down the diagonal, 24 times a plus sign times e to the x gives me plus 24 e to the x. And now I've reached the bottom. This diagonal hit the bottom row on the dv column. So I'm done. I add my constant of integration. And there's my answer. And for those of you, if you think back to our last video and multi-step integration by parts, you can probably imagine how much writing we would have had to do in order to get this answer using that technique. So tabular integration can be really, really helpful for us as far as saving the amount of writing that we need to do and all of that. So that's going to bring us to the end of this video. We're going to come back with one more video on this topic. We're going to work through a couple of more examples using tabular integration, go through the entire process from the start. And then we'll be done with integration by parts. All right, everybody, have a great rest of your day, and we'll see you next time. Bye-bye.